Okay, so here's the question that we considered last time. We made a bunch of progress on, and that is, suppose you are moving along a curve like this, curve in R2 or R3, right? And suppose you are interested in keeping track of how a certain function is changing, right? So you're interested in computing this quantity of change. And the question is, in keeping track of how that function is changing as you move along the curve, kind of like what happened when we were thinking about the fundamental theorem of calculus, do you get any nice results out of it? Let's just try to emulate the argument that we made here in the context of the fundamental theorem of calculus. And, can we reproduce that if we just kind of cheat, steal the flow of ideas in this new context? Does anything actually come out of it? And the answer was yes. We have this fascinating result down here called the fundamental theorem of line integrals. It kind of cosmetically looks a lot like the fundamental theorem of calculus, but this addresses a very different scenario. Namely, not, coming back to the fundamental theorem of calculus, can I compute a Calc 1 integral? Oh, good news, yes I can. It's f of b minus f of a. Now it's, can I compute a vector line integral? That was a pretty different thing. And the answer is yes. It's f of b minus f of a, suitably interpreted. So we saw some examples of this last time. The big point to keep in mind in that analogy of how to use this for computation is that it is simply not always the case that a vector field is actually a gradient of something. Look over here what the fundamental theorem says. This does not say a line integral of any old thing. This has a line integral, a vector line integral, specifically of a gradient field. Not all vector fields are gradient fields. Coming back to the fundamental theorem of calculus, how many functions can we say are actually derivatives? Well, the great news is most of them in some, suitable sense, specifically all continuous functions are derivatives. So, in some sense, practically all the time, this is fine for the fundamental theorem of calculus. For the fundamental theorem of line integrals, it's not. This is a big worry. Is our integrand actually a gradient of something? We got to worry about that. Okay, so the first computational example I showed you, I just I kind of bypassed that question, and I just here we go. We want to compute a line integral. Here's our vector field, and I just pulled out of thin air. Yeah, it is a gradient, and furthermore, this is the anti-gradient. That's the function whose gradient is our given vector field. So I took an example where everything's fine, it actually worked, and furthermore, the anti-gradient was, dare I say, given in terms of how I presented this example. Okay. But this example does illustrate the mechanics of how you're going to use the fundamental theorem of line integrals, at least in the cases where you know the anti-gradient, and that is identify your vector field as being a gradient, find the anti-gradient, and use that anti-gradient to plug in the for f of b minus f of a, as it were. Plug f of the endpoint minus f of the starting point. Okay. All right. So now let's go on to the natural next question to ask. What if we don't have a freebie anti-gradient given to us? How do you find that anti-gradient? Here's a procedure. There are different ways to do this. This is, I think, the most easily understood. This is the most natural way to do it. Our big question is our vector field. Keep in mind our vector field is got components PQR. Is our vector field a gradient of something? Well, of course, that's what a gradient looks like. Gradients are have components that are partial derivatives. That question, is our vector field a gradient? You can view it one component at a time. You can ask, well, is P the partial of f with respect to x? Well, I make the innocent observation that if P is the x partial of f, then f is the x antipartial of P. Right? I mean, that's the same statement pretty much. asterisk. Okay, sure. Don't forget, whenever you rewrite a statement about derivatives as a statement about antiderivatives, you do have to throw in the requisite plus C, because of course, when you take a derivative of a constant, you get 0. It goes away. It's so you kind of that it could be there. This constant could be here, and you would never notice it in that statement about derivatives because its x partial is, well, 0. So the slight twist that you have here is that, well, in this context, since we're taking a partial with respect to x, this need not actually be a constant. It just needs to be anything whose partial with respect to x is 0. And so, in other words, it could be any function of y and z. It could be any function anything that doesn't have x's in it. Okay? And so I think it's not hard to persuade yourself. This is you definitely want to make sure to think this through. That P being x partial of f is simultaneous with equivalent to f being the x antipartial of P plus a function of y and z. And then likewise for the other coordinates. So this Q would have to be the y partial of f. Well, that means f must be the y antipartial of Q. Plus anything whose y partial is 0. In other words, any function of x and z. And then likewise, the R component if it's going to be a z partial of f, then f has to be the z antipartial of R. Okay. All right, so roughly speaking, here's how we're going to find, keep in mind our goal is to find this function. We want to find the antigradient. We want to find this thing. Assuming it exists, right? Fingers crossed. Well, what we've figured out by rewriting this statement as that statement, what we figured out is that f has to be all three of these things, and these are things I can compute. And it's just a matter of plug and chug. So here's an example. Let's just get our hands dirty. Why am I still zoomed out? Let me zoom in. Okay, so let's find the antigradient of this vector field. Again, fingers crossed, we hope this antigradient exists. How am I going to find the antigradient? Well, this is our P. That P needs to be the x partial of our function, and therefore the function f we're looking for is the x antipartial of it. So there's our first statement. Oh, wait a minute. Of course, it plus any function of y and z. Right. So proceeding, as we did before on the previous page, that y partial, its y antipartial has to be f, and this z partial, well, its z antipartial has to be f. So the mystery function that we're looking for needs to be all three of these things. Now, these being our general formulas, these being the antipartials that come up in this example, these being the, if you actually compute those antipartials, the functions that you actually get, they're not all the same. Right? Look at these two happen to be the same, but the third one isn't. And so there's a temptation to throw it out and say, nope, didn't work. These things are different. But don't forget about the mystery constants, right? We can have certain partial constant, you might say, functions over here. And those are allowed to play in the game as well. And so what we really have then, I've got too many little dots accumulated there. What we really have is a question of, can I play some game, some way, somehow, to make these constants in such a way that all three of these things are equal? And yeah, you can. It's a little puzzle. You got to play the puzzle. Right? Think strategically. How can you make this work? And the way to make it work is no problem. Just let this function here be yz. And then notice that all three of these are xyz plus yz. Everybody's happy, everybody wins. And then these you just make these 0. So, in fact, there is a function that is all of these antipartials. And therefore there is a function that is the antipartial we're looking for. Yeah.
Could you have made C2 and C3 negative YZ? And that would
no, I hear where you're coming from. So let's ask the question, can I make this negative YZ? And the answer is no, because it's not allowed to have Y's in it. Right? It's explicitly got to be a function of X and Z. So you have to do it the other way. You have to make this YZ, and you're allowed to make that YZ because that is strictly a function of Y and Z. Yep. It's a great question. Thank you for that. Does everybody see what her question was and what the answer is? Yep.
So then, should the thing on the bottom actually be C2 or X and Z or not?
Oh gosh, yeah. Oh man, how did I not? Okay, I must have been distracted when I was writing this. This is X and Z. Thank you for noticing that. And then this is X and Y down here. I was spaced. Thank you for noticing. Yeah. Yeah. Okay. Right. Okay, so we have our anti-partial. And so if you were asked at some point to find, some vector line integral of this vector field, it's not given as a gradient, but you can view it as a gradient of this thing, and therefore you can use the fundamental theorem of line integrals, which again, highly desirable compared to the plug and chug pullback method that we've talked about. Okay, so is this always going to work? Answer: no. Again, sadly, not every function is a gradient of something. Excuse me. Not every vector field is a gradient of something. Not every vector field has an anti-gradient, unfortunately. So when's it going to fail? Well, this is where those theorems that we talked about, sans context, back in 15.1. They're really very useful. Let me just remind you, and I haven't justified these theorems here yet. I'm going to give you some context and some justification, the point of view anyway, a plausibility argument for these statements later on as we develop more tools. But the assertions that I've made for the moment, and you're allowed to use these, are that looking at this diagram, everything has a lifetime of 2. And so, in particular, notice that means 2 things. For one thing, if you have a gradient, then Green's operator will give you 0, but more to the point. If Green's operator gives you 0, then that thing is a gradient. And likewise, if Green's operator is not 0, then it is not a gradient. So Green's operator is the perfect test. This thing here is the perfect test of whether or not you're looking at something that came from the gradient operator. So nice rule. Just compute Green's operator of your vector. Whatever vector field it is that you're interested in, you'd like to know if it's a gradient or not. Compute Green's operator and see what you get. And this will resolve the matter for you. Side note: there's going to be some analogous versions of this. One we can talk about already is looking at this part of the R3 diagram. Same deal. Again, gradient is composed with, well, this next thing. Well, it's this curl operator in the R3 context. Now, again, what is curl? As of right now, it's a formula. I haven't given you any context or geometric sort of intuition of what curl means. It's coming. We're going to crush that, right? We're going to talk about that a lot, but right now it's just a formula. And you may take my word for it at this stage that if the curl is 0, then there is an anti-gradient, and if the curl is not 0, then there is not an anti-gradient. And again, it's just sort of the lifetime of 2 point of view on these diagrams. Again, justifications to come later on. So here is an example. Let's look at this vector field here, and let's try to decide, is there an anti-gradient to this vector field? Certainly it's not obvious, right, from any sort of, intuitive standpoint at a glance. You could play the game. You could start taking anti-partials like we did for the last vector field. Start doing this kind of thing. Right? See if you can make the puzzle work. Right? Or alternatively, and I think this is a healthy exercise, is start writing down the curl. right? This is a three-dimensional vector field, so we're considering a three-dimensional vector field, so this is what we're talking about, more to the point, this is what we're talking about. So curl is the operator to consider. Start computing the curl. Right, we have these formulas for curl. Start writing it down. And by the way, notice very quickly, the first component that you compute, you get not 0. And there's a nice consequence of one of the components being not 0. And that is, it doesn't really matter what the rest of the components are. There's no way that this vector is the 0 vector. It has a component that is not 0. Therefore, as a vector, it's not 0. If as a vector it's not 0, then I already know there is no anti-gradient. So no, there's no anti-gradient. I don't even need to compute the other components. In fact, notice you can kind of do this whole process in your head, right? Let's notice, this calculation, Ry minus QZ. The y partial of that, you can just see it. 2yz plus 1. The z partial of that, 2yz. Those aren't the same, therefore their difference is not 0. Not 0 there means not 0 as a vector, and that means there is not an anti-gradient. At a glance, right? You don't have to write out a bunch of partials and start playing puzzle games. Okay. Now, let me emphasize, let's suppose that these functions were different somehow, some different functions, and let's suppose that, of course, the calculations can be different. Let's suppose you got 0 here for your first component. Can you just, drop the pen and walk away and declare victory? No, because this doesn't resolve the matter. It is possible that we will get the 0 vector out of this. It is also possible that we will not get the 0 vector out of this. One of the components being 0, it just doesn't resolve it, right? It could still go either way. It's only when you get non-0 that the matter is resolved. Okay. Alrighty. So the next 2 pages represent some ideas that are not in the book. And let me just. So there's some difficult ideas that relate to the theorems that we're going to talk about in this chapter. And it's really fascinating discussion. It's very sophisticated discussion. It's well beyond what we can realistically do in Math 212. Which puts us in a tight bind in terms of how to teach this class. We can't tell you the whole story of how Chapter 15 theorems are all ultimately the same, one single, unified, huge theorem, because it's just beyond our reach, realistically. Well, then we can present all the theorems in Chapter 15 as just being separate theorems. And you can do that, and that's what the book does, approximately. But there's something really sad and disappointing about that, because the fact that theorems that we haven't talked about, you don't know what I'm talking about yet. I'm sorry for that. But there's a bunch of theorems that we're going to see here in Chapter 15 that are, they're so similar. They have so much in common. How much you understand one of these theorems is going to be really, really helpful if you see the analogies, if you see the connections between the theorems, really helpful in understanding the other theorems, right? So there's tremendous value in talking about the connections between these theorems, even if I can't tell you the whole story. So what I've got here, and again, this is my little cheat, my approach to this quandary. Is to make a sloppy, non-rigorous, I'm going to call it a bookkeeping method, right? A way to organize ideas just sort of structurally in your mind, and in a way that will allow for you to see the pattern. There is a tremendous pattern. It's highly visible if you look at it just the right way. So I want to look at all this stuff in the way that allows you to see the patterns, even though there's a tremendous amount of stuff that I'm not going to define at all, or I'm going to define in very, very sloppy ways, deliberately. Right? just for sort of pattern purposes. So anyway, here's what I've got. There's a certain point of view on the fundamental theorem of calculus. Here are some of the objects that we play with when we talk about the fundamental theorem of calculus. There are points that I can plug into functions, like so. And it seems like a silly, trivial observation. Yes, that's what functions do. If you have a function, you can put a point into it. Out comes the value of the function. Anyway, for the record. Then here's another thing that we have. If you give me a function, let's just say, and then if you give me an interval, here's a different thing I could do. With an interval, I can ask, what is the integral over that given interval of that function as the integrand? That's another kind of what I call evaluation. It's another thing you can compute given those inputs. Okay, so I'm going to call this column 0 in the sense that the points that we're talking about, these are just points. They're 0-dimensional. So thus column 0. Again, this is just for organizational purposes. I'm being deliberately vague, right? So please don't ask me for rigor in this. That's not what we're doing here. Likewise, I'm going to call this column 1 because here we're talking about a one-dimensional interval. An interval on the x-axis, that's a one-dimensional thing. Okay. All right. Here's another thing that we have. We have the idea of boundary. Right? If you give me an interval, then we can talk about the endpoints, the boundary. Where is that interval? Where's the edge, if you will, of that interval? And there's two boundary points. There's a starting point and there's an ending point. So, given an interval, there are corresponding boundary points. I'm going to think of that as an arrow that goes that way. Okay. Again, this is all just sort of bookkeeping. Where I'm not being rigorous about any of this. Okay, so here's the question I want to ask. This is the question that the fundamental theorem of calculus answers. Here it is. Suppose you have a function there, and suppose you have an interval there. I ask the following question. Suppose you were to take the boundary of the interval, plug that into the function. In that sense, you get some number. Is there sort of a complementary operation that you could do to the given function such that the resulting integral would give you the same value? Right, so we want to ask the question, so here's the big question. Does this operation exist? Is there a way to do something to the given function in column 0 that makes this pattern work? And yeah, there is. It's as you can see right here in the diagram. It's the derivative. Right? If you take a derivative and do an integral of it, what you get is the same as if you evaluated the function at the boundary points. Now, there's our fundamental theorem of calculus. The derivative, do an integral of it, plug in the boundary points into the original function that you took the derivative of, you get the same thing. Okay. So anyway, now that's just a pattern. What is this worth to you as of the moment? I have not been at all persuasive as to why you should care about this yet. Right? It's a way you could lay out the players in this story called Fundamental Theorem of Calculus. What I'm going to claim now, and this is just a claim, you'll see this play out over the next several weeks. I claim that this pattern holds in a variety of other circumstances that we're going to see. This is a common theme in most of the big theorems that we're going to see throughout the rest of this chapter. So the reason I show you this, how I've got these items laid out on the diagram and how the pattern of the theorem shows up on the diagram is so that you can be on the lookout for this, so that you can see the comparisons and analogies between these various different theorems as we go through the course. So you'll be learning those ideas in a framework as opposed to just sort of in their own separate little sort of insulated contexts. And I think there's a lot of value in this. Okay, so just a little bit of a preview. Here's what the diagram is going to look like when we're looking in 2 dimensions. You've already seen part of this. You've seen how I have claimed, without much demonstration, I've claimed that it makes good sense to compose the gradient operator and Green's operator. And I've just sort of asserted that. Right? Well, hey, if I have a 2-dimensional region, I appeal to your geometric intuition. The boundary of a 2-dimensional region is, if you think about it, a 1-dimensional curve. And if you were to take the boundary of a 1-dimensional curve, it's going to have endpoints, namely 0-dimensional points. So we have this, again, this idea of a boundary operator. We have existing operations. You can plug into functions, you can plug points by that formula. Into into curves, you can plug vector fields to compute vector line integrals. Into functions, you can plug regions in a certain sense and compute double integrals. These are various operations that make sense on these contexts, and it's going to turn out that the pattern's going to hold. We've already seen one of them. Here it is, fundamental theorem of line integrals. Fundamental theorem of line integral says if you take a gradient and compute the line integral of it, that's the same as looking at the boundary points of the curve and plugging into the original function that you took the gradient of. In other words, that these are equal. In other words, fundamental theorem of line integrals. Okay. All right. That pattern is going to hold in this context. We won't get to that today, but there is a 2-dimensional version, you might say, of the fundamental theorem of calculus. And there's a 3-dimensional, there's kind of a couple of 3-dimensional versions as well, and we're going to talk about those later on. Okay. Oh, yeah, here's what the 3-dimensional diagram looks like. By the way, it starts to get pretty hairy. Right? Look at all those symbols on the page. All of these, everything that's on this page is something that we need to study in Math 212. The diagram here is showing you the organization of those ideas. This is showing you patterns that will help you organize those ideas in your mind. This is not this is not additional ideas that you have to digest. This is a tool for digesting the stuff that we have to digest anyway. Right? So anyway, I claim that these patterns hold, and we'll again, lots of discussion is going to go into each little tiny part of this diagram. Okay, so we're going to watch this build over the rest of this course. Okay, so before we go on to the next part of the diagram, I want to talk about an idea relating to vector fields called path independence. Path independence is a property of a vector field. It's a remarkable property. The way I'm going to present it deliberately here on purpose, first cut, it's a property of a vector field that should kind of sound impossible. This is a big eyebrow raiser. How could this be possible? Remarkable feature that a vector field might have. Here is the property. If I were to say that a vector field is path independent, here's what I mean. Given any 2 points that I interpret as starting points and end points, I could talk about, for example, what the line integral of that vector field is along, let's say, that curve. I could talk about the line integral of that same vector field along that curve. Or I could talk about the line integral of that vector field along that curve. There's a bazillion different curves that you could use to get from the agreed upon starting point A to the agreed upon ending point B, right? Well, there's so many different curves. These curves, if I were computing line integrals on these curves, on those line integrals, on this green line interval, we're looking at the vector field over here. On the blue line integral, we're not going anywhere near those points. Rather, we are going to include a bunch of these points that the green curve doesn't go anywhere near. Right? you could just imagine, the mind reels at how many different paths you could use to get from the agreed upon starting point A to the agreed upon ending point B. So a path-independent vector field would require, and this seems highly unachievable, highly intractable, would require that the line integral along the green path, the line integral along the blue path, the line integral along the orange path, the line integral along any path that you can think of from A to B. I mean, no matter how wacky and squiggly, right? No matter what path you pick, the value of the line integral has always got to be the exact same thing. How could that possibly be? If you think about it, just at a first glance, right? There's infinitely many requirements. There's infinitely many different curves from A to B, so there's infinitely many different requirements on the vector field. So many different integrals have to all be the same. This seems just implausible that a vector field could do this. Does everybody see the point of view on this? That it just, I mean, come on, how could this be possible? Okay, this is highly possible, as it turns out. And this is one of these situations in math where once you take the right point of view, you realize not only is it highly possible, but it's borderline obvious. I had a conversation with a colleague one time. I was thinking about, this is an aside, sorry, but this is funny. I was talking with a colleague, and I had this idea in my mind that a certain thing ought to be true, and I felt like this ought to be true, and I couldn't figure out how to prove it, and I wasn't sure if my intuition was right on this, and I talked to a colleague, and I said, so here's what I think is true, and he said, no, that's not possible. That's not possible. Oh, no, wait, it's obvious. Right? So sometimes stuff like that, and he was right, by the way, it was obvious. Just being thick. So this is highly possible, and here's how I know that this can be done. The fundamental theorem of line integrals actually gives us a bazillion examples of this in action. Now, let me remind you of what the fundamental theorem of line integrals says. Fundamental theorem of line integrals says that the integral of a gradient along any curve dot dx is f of b minus f of a. Okay. Well, if we agree upon and fix these starting points A and B, then whatever vector field, whatever gradient field we're talking about, along all of these different curves, this line integral is all going to give you the same value because on all of those different curves, I have the same starting point and the same ending point. Right? Pick any curve, I don't care. Any curve at all that starts at A and ends at B. I can evaluate this gradient line integral as, well, f of b minus f of a. Oh, what if I pick a different curve? Well, it's still going to be f of b minus f of a. A and b are fixed. We're looking at the gradient of the same function, little f. The right side is completely independent of the curve. Depends only on the endpoints. Right? So the moral of this story is that every gradient field is path independent because for every gradient field, the line integral depends only on the endpoints. So again, at a glance, path independence seems like an impossibly difficult challenge for a vector field to achieve. And then you look at the fundamental theorem of line integrals and realize, oh, it's not only is it not impossible, but here's a bazillion examples. Every gradient field has this path independence property. Okay, so I think this is a wonderful little mini discussion. I think this is a really big idea. I want to encourage you all to spend time thinking about digest this idea that path independence, this feature of a vector field of path independence is very closely wrapped up with the idea of the fundamental theorem of line integrals and gradient fields. A lot of good ideas to digest here. All right, now some harder things to show. Not only is every gradient field path independent. It's also true that every path independent field is a gradient. Now, again, let me just remind you, we're ignoring issues about irregularity. So we're assuming that all the functions, all the fields, everything in sight is continuously differentiable, infinitely differentiable, well-defined everywhere. We cannot have any buts, no little micro, at this one point it's not defined. No, nothing. It's got to be perfectly fine. No problems with regularity at all. Otherwise, all this stuff comes crashing down. It becomes a much more complicated discussion that we aren't going to go into. So with that asterisk, as long as everything in sight is fine, every gradient is path independent. Okay, so gradient fields and path independent fields, in fact, in this highly regular context, they're the same things. They are the same fields. Okay. All right. So here's my little summary of it. We know that every gradient is path independent. Every path independent is a gradient. That's nice. Oh, reminder, don't forget what we already knew. We already knew that every gradient had curl equal to 0, and if curl is equal to 0, it's a gradient. So we already knew that these were equivalent. Now I'm adding that these are equivalent, and so by transitivity it follows that these are equivalent. This is a weird little result we've got here. Now we have 3 different descriptions of what are, in fact, exactly the same vector fields. This brings up the question, well then why do we have 3 names for them? Right? Why don't we just pick a name and stick with it? Right? So very importantly, there's a great answer to that question. The reason that we have different names that describe what are in fact the exact same fields is that we're not describing the collection, this specific collection of fields. We're describing a property that they have. So what we have here is really a collection of fields that satisfy 3 very different properties. Right? So the property of a vector field being a gradient of something, algebraically, that's a very different property than the property of path independence. The way you would describe path independence is extremely different from the way you would describe curl being 0, which is very different from the way you would describe being a gradient. So we need to have these different descriptions because the properties themselves are what's interesting, and the fact that any vector field that has one also has the other is really a motivation to talk about the distinction between the properties, not the other way around. Okay. Alrighty. Okay, so here's an example. Let's talk about why we care about a vector field being path independent. I'm going to give you 2 different points of view on that. First, the first one, just let's not get ahead of myself. Suppose I want to compute this line integral. Y'all are accustomed to the motivation for wanting to compute things. So here's one. Let's suppose I want to compute something. My vector field is given. My curve, my domain for the line integral is given. Top half of the unit circle, counterclockwise, our old friend. Right? How would I compute this thing? Well, you've got a couple of choices. I mean, one thing you could do is you could brute force this. Again, don't forget that so our first perspective on how to compute vector line integrals. Brute force, right? Parameterize that curve. I know how to parameterize that curve, right? And we could plug in and pull back stretching factor, right? And plug and chug. So anyway, you could do that, but let's not. So here's what I'd like to do. First of all, let me observe that Green's operator, right? I can compute Green's operator of that vector field. I get 0. And therefore, our vector field is path independent. Well, we could say this different ways. Therefore, it's a gradient, and we already know every gradient is path independent. So, this is path independent. This vector field is path independent. That's a powerful observation. Coming back up to here, what does path independent say? Path independent says, pick any curve you like. Well, it's got a start and end at the given points, right? I mean, obviously, you can't pick, don't pick that curve. right? We've agreed that we're starting there, we're ending there. But with the understanding that you can't change the starting and ending points, pick any path you like. The value of the integral is not going to change. It's whatever, it's independent of your path. So looking at this question, I get to change this curve. Because we're looking at a path-independent vector field, I could change that curve to any curve I want. That starts and ends at the same point. So here we go. We were given originally, that was our given curve. I'm going to cite path independence. So understanding, I've got to start and end at the same point. Can't change the starting and ending point. But other than that, I can pick any curve I want. And here's some options for us to consider. Right? We can do whatever we want. I could pick this curve if I wanted. Perfectly fine. Knock yourself out if you want to. Anybody like that curve? I don't like that curve. That looks like work. It looks like effort. It looks like computational inconvenience. So I'm not attracted to that curve. You could pick that curve if you wanted to make it, seemingly a little straighter. But let's cut to it, right? What's the curve that we like best? What's everybody's favorite curve that starts at that point and ends at that point? If you're anything like me, that's your favorite curve. That starts at the left purple point and ends at the right purple point. And by virtue of path independence, I can change to that curve cost-free. Line integral is not going to change. Okay, so phooey on the original curve. I've got a new curve on which I want to compute the line integral. All right. Now some geometric observations on that curve. Again, here's a phooey on the original curve. We don't care about that anymore. We are now looking at that curve. Notice, observe, y is equal to 0 everywhere on that curve. The computation that I'm doing, every point along this path along which I'm doing the integral, for my entire calculation at this point, y is 0. So let's take that and plug it into our vector field. Y is equal to 0. And that means that our vector field simplifies to that on our new curve. Now notice that wasn't true of the original curve. In the original curve, y was all kinds of not 0. On our new curve, cleverly chosen, y is 0. Our vector field simplifies. Okay. Knowing that our vector field is this, let's draw a picture of what 0 comma x squared looks like. The first component is 0, and that means it points straight up, like that. My dx vector points, let's see here, I made some, okay, fine. Our dx vector points along our curve. Notice that these are always perpendicular. Therefore, this dot product is always 0. I'm adding up a bunch of zeros. And so my answer is 0. And we are done with, minimal effort, minimal calculation. How about that? Any questions about that? Everybody see what happened? So, every so often you get lucky in, using path independent. Changing from one curve to a different curve makes your calculation simpler. Yeah, did you have a question? Oh, okay. Yeah. Anybody else? All right. Now, so my goal with this example was to try to persuade you of how useful this idea is. I'm making the pitch for why this is a good thing. Now let me make the counter pitch. Let me try to detract from my own point. And then I'm going to detract from my detraction. I just want to, kind of show you the arguments on both sides. Here's the thing. Using path independence, yeah, that was nice. This argument worked out nicely. But how did I know it was path independent? What was the foot in the door for using path independence? Well, the fact that it was a gradient, which I got from, Green's operator. But here's the thing. If it's a gradient, we could have used the fundamental theorem of line integrals. we could have found an anti-gradient, and we could have, this would have been, an easy anti-gradient to find. Right? Start taking anti-partials, play the game. It's an easy game. You win the game, and then you plug in to the fundamental theorem of line integrals. So a case could be made, and this case is made regularly, that this is that's kind of like a superfluous tool in your toolbox, right? We already have a really good screwdriver. This is pretty much the same kind of screwdriver. If you already have an outstanding screwdriver, right? How much is another screwdriver really worth to you? I already have a screwdriver. I don't need to go out and collect multiple kinds of screwdrivers. Well, even if they're the same kind, I just don't need to have multiple Phillips head screwdrivers. Right? One's enough. So the case could be made that, who cares? Now let me make the rebuttal to that. Why do we care about a tool if we already have effectively an equally applicable tool? And the answer is because computing stuff is not our only goal in this area. So I want to show you another discussion for which we really need the notion of path independence. So it has to do with physics. By the way, if you haven't had a intro course in physics, no big deal really. But hopefully you all have seen from high school, I don't know, with physical science or whatever they call it in high school, the idea of conservation of energy. So very quickly, the idea of conservation of energy, and I don't mean from an ecological, energy, national priorities sort of standpoint. What I mean is this assertion that energy is neither created nor destroyed. So, for example, kinetic energy plus potential energy is a constant in mechanics. Easy classical first example. Consider this pen. That pen is not moving. It has no kinetic energy. If I were to drop it, right, and I don't want to because it's going to fall and splat and fly somewhere, and I don't know. But if I were to drop this pen, right, very little effort on my own, and moments later it would be down to this altitude, moving at quite a bit of speed. And so what happened there? How did the zero kinetic energy that we look at there turn into, effortlessly on my part, a large amount of kinetic energy when it was down here? Did that kinetic energy just spontaneously generate? And the point of view is that no. What we have up here, when the pen's up here, is there's no kinetic energy, but there's a lot of potential energy, what we call potential energy. Where did that potential energy come from? The potential energy that I claim sits inside of this pen right now. It came from my process of lifting the pen. How when I picked it up, think back to, earlier in section 15.2, as I pick up that pen, I'm doing work. I'm burning calories ever so slightly. Burning calories and lifting that pen up to this height. And the work that I put into lifting it stores potential energy in the pen, and then when I drop it, however much potential energy I gave it is converted into kinetic energy as it falls. So that's the idea. And so, the kinetic energy might go up or down. The potential energy might go up or down or up. But in total, it's constant. Okay, so this is a fundamental idea in mechanics. But notice this idea of conservation of energy. This is a tremendous idea in physics. It's a huge idea. It's an indispensable idea in physics. Relies on the existence of this thing called potential energy. And how do you compute potential energy? Well, per my little discussion there, potential energy is the amount of work that I put into something as I lift it. The amount of work that it takes to move this pen along a path. And the amount of work that it takes to move it along a path from a starting point to an ending point is a vector line integral along whichever curve you pick. Well, if I want potential energy to depend only on my endpoint, given a certain starting point, I mean, that had better be the case, right? If I want to talk about the potential energy of the pen at that point, potential energy better depend only on the point, the location. Potential energy had better not depend on which path I pick. The work that it takes to move along the yellow path had better be equal to the work that it takes to move along the green path, because the one work and the other work both have to equal to potential energy. Both of those works are line integrals. That means that the vector line integral along this path and the vector line integral along that path have to be equal. Right? This yellow work calculation, this green work calculation, they better be the same thing, because they're both required to be equal to potential energy. So, punchline then, the two line integrals have to be the same, therefore the vector field has to be path independent. Purple. So this is a big observation, and why do we need this notion of path independence? Tools in a toolbox. I already have a screwdriver. Why do I need the screwdriver? Path independence is the idea that allows us to generate this concept of potential energy. You can't have the concept of potential energy without talking about path independence as an idea, right? So, as a computational tool, okay, yeah, sure, right. Maybe it's not as essential. That's not its job. This idea of path independence, among many other things, allows us to create this extremely powerful concept of potential energy that allows us to come up with from that this extremely powerful idea of conservation of energy. And if you focus on, but how do I compute stuff, you miss these tremendously powerful ideas. So anyway, that's why we need to care about path independence. And this is a good stopping point. We'll pick up here next time. Y'all have a great weekend. Don't forget to turn in your homework right over here. Oh, and as usual, if you came in after I finished calling attendance, make sure I get you marked down.